6.1 is all about exponents. Exponents are something you probably learned about in Algebra 1. But we're going to take some time and review it. First of all, the basics of exponents. Let's talk about x to the fourth power. Now, the x part is the base of the exponent. And that brings us to the 4, that is the actual exponent. Now, what do exponents mean? X to the fourth actually means, I'm sure most of you know it, x times x times x times x. Whatever the base is, you multiply it by itself, whatever the exponent, that many times. So, along with that, there are 7 rules. There are 7 exponent rules, and we're going to learn about 2 tricks as well that I kind of came up with. First of all, let's talk about the 7 exponent rules. 7 exponent rules, and again, you've probably seen most of these at some point. We're just going to kind of refresh your memory about them. The first exponent rule: a to the m times a to the n equals, now if you guessed it, great, but here, let's do an example here. Let's suppose that I had 5 squared times 5 to the third power. Well, again, what does 5 squared mean? It means 5 times 5. That's this part, right? And then 5 cubed, that means times 5 times 5 times 5, which is that part. So we have a total of 5 to the 5th power. So how did I get from 2 and 3 to get to 5 to the 5th power? We added the exponents. So this would be a to the m plus n. A to the m plus n. And this here is like a little proof of why this is. Our second exponent rule: a to the m quantity to the n power. Let's think about this one. Again, if we had 5 squared quantity to the third power, well, think of this as the first a. So what we got here is 5 squared times 5 squared times 5 squared. This, what's inside the parentheses, to the third power. So if we got 5 squared times 5 squared times 5 squared, from the previous rule that we just learned about, a to the m times a to the n is equal to the sum of those exponents. 2 plus 2 is 4. 4 plus 2 is 6. So we had 5 to the 6th power. So here, how did I get from 2 and 3 to get to the 6th power? We multiply them. A to the m times n. Third rule. Third rule. It's very similar to the previous one. AB quantity to the m power. Well, let's think about this one. If I have 5x to the third power, that means 5x times 5x times 5x, which is, well, how many 5s do I got going on here? 5 times 5 times 5 is 5 to the third power. X 3 times, x to the third power. So we had 5 times x to the third power. Each one of them got to the 3, so it's kind of like the distributive property. Not really distributive property, but it's, oops, not just 5 to the third. Here it's a to the m times b to the m. They each get the m exponent. Cool. Well, fourth one. This is very similar to number 3. Let's talk about this one. A over b quantity to the m power. Now, for some people, you don't even got to think about that one, right? But let's think about it for a minute. 2/3 to the third power. That means 2/3 times 2/3 times 2/3. And when you multiply fractions, top times top, for a total of 2 to the third power over bottom times bottom. 3 to the third power for a grand total of, this 3 gets distributed to both the top and bottom. Both the numerator and the denominator get raised to the power that's outside. Again, it's kind of like a distributive property, but not quite. So this is a to the m over b to the m. The fifth rule that we're talking about can actually be kind of thought of from rule 1. Rule 1 was a to the m times a to the n, and look what happened there. Here we're going to do a to the m divided by a to the n. Well, when we did this, when we did a to the m times a to the n, what did we do with those exponents? We added them. So here, what multiplying is to add, dividing is to, you may have guessed it, subtraction, a to the m minus n. Smith, are you sure about that? I don't know if I buy that. Let's do an example. 5 to the 6th power over 5 squared. Let's talk about that. Well, 5 to the 6th power means 5 times 5 times 5 times 5 times 5 times 5 times, how many is that? 6 of them. Good. Divided by 5 times 5. What's going to happen here is these 5s are going to cancel out. Since it's all multiplying, and we're dividing, they can cancel out, and we're left with 5 to the 4th power. Well, how did I get from 6 and 2 to the 4th power? We subtracted them. 6 minus 2 is to the 4th power. So, 5 rules down. That means there's only 2 left to go. And these last 2 are kind of abstract for some people. A to the 0 power is, no, it's not 0, it is 1. A to the 0 is 1. Anything to the 0 power is 1. Let me give you a little proof of that. Let's talk about 5 to the 6th power divided by 5 to the 6th power. We could go and list out a bunch of 5 times 5 times 5 times 5 over 5, 5, 5, and you'll see they'll all cancel. Or think of it this way. Something divided by itself is always 1, right? 6 divided by 6 is 1. 5 divided by 5 is 1. X divided by x is 1. But here, when we subtract them, we get 5 to the 6 minus 6 from our previous rule. And that shows us that 5 to the 0, and as we said, anything divided by itself is 1. Anything divided by itself is 1. A to the 0 is 1. And that brings us to our last rule. The 7th rule is a to the negative m equals, now, back here we talked about a bunch of positive exponents, just positive numbers. We talked about 6 divided by 2, that got us 5 to the 6 divided by 5 squared. We did 6 minus 2 and we got 5 to the 4th. But what if that's flipped? What if I have 5 squared over 5 to the 6th? Well, let's list them out. What if we had 5 times 5 over, and we got the 6 5s here. 1, 2, 3, 4, 5, 6. The 5s cancel. And I'm left with 4 5s in the denominator, or 5 to the 4th power. Well, what's on top? We got a 1. Right? Well, let's use our rule 5 here. 5 to the 2 minus 6 is 5 to the negative 4th power. But if we list them out like this, we can see that 5 to the negative 4th power is actually 1 over 5 to the positive 4th power. And that's what's happening here. A to the negative m is going to become, if you have a negative exponent, it becomes a fraction. Negative exponents make a fraction, and we're going to have a to the positive m in the denominator. It bumps down. So those are our 7 rules. What I'm hoping I kind of did here was kind of provide a little proof for you. It's not the most colorful thing this time, sorry y'all, but hopefully it kind of sketches out why these rules are the way they are. And let's do one quick example. Let's go with x to the 4th times y to the 3rd times x to the 7th over the quantity x squared, y squared, quantity to the 5th power. Well, if you use your rules here, let's just take care of the top. Don't even worry about the bottom yet. The top looks like we got the first rule going on here, right? A to the m times a to the n. In this case, x to the 4th times x to the 7th is x to the 11th power, and y to the 3rd. The bottom is going to be x to the 10th. Sorry about the bleeding right here with the marker, divided by y to the 10th. So this brings us to one of the first tricks that I like to use. Look at the x's. I got 11 x's on top. I got 10 x's on the bottom. Who wins, top or bottom? Well, if we have 11 x's, we could write them all out and start canceling stuff. 10 of them would cancel, but ultimately the top would win by 1 because there's one extra x up there. But what about the y's? You got 3 y's on top, 10 y's downstairs. Who wins? Well, the bottom wins by 7th. And that's our final answer. We take this big mess here. It turns into, or we only have one of each variable. And the other thing is, we want one of each variable and only positive exponents. Our final answers are only going to have only positive exponents in them. Which brings me to my second trick. And this is called the bump trick. Oops. The bump trick. The bump trick says this. Negative exponents bump to the other level and become positive. Negative exponents bump to the other level and become positive. What does that mean, Smith? I don't even know what you're talking about. All right, let's do an example. Draw a fraction bar. We're going to have x to the negative 3rd, y to the 8th, z to the negative 4th over m to the 6th, g to the negative 8, p to the negative 3rd. All right, so as we said before, our final answer should only have positive exponents. If you have a negative exponent, something's got to be fixed. And the easy way to do this is with this bump trick. What you think about is, are they happy where they're at? X to the negative 3rd. Negative 3rd, you think he's happy there? No. He doesn't like being on top. So X bumps down, bumps to the other level, and becomes positive. He was on top, he bumps down, becomes positive. Let's see if I can write this better. X to the 3rd. What about Y? Is Y happy on top? Sure. Y loves the view. Z, not so much. Z bumps down and becomes positive. What about M? Well, M is positive. M likes it just fine downstairs. Whereas G is downstairs in the basement and he don't like it. He wants to go upstairs. So G to the 8th power. And P is another one who wants to bump up. He's negative downstairs. He bumps up to the other level and become positive. So the bump trick is an easy way, if you have negative exponents, to make your final answer so they have just positive exponents. So what we've done here is I've given you 7 tools and 2 tricks. Again, the 2 tricks are, this one I call like the who wins, and then I got the bump trick. So we got 7 tools and 2 tricks. Tomorrow in class, I'm going to give you a bunch of problems. You apply these 7 rules and simplify exponents.